Welcome to the Gardien Group Podcast Series. The Gardien Group, providing extraordinary solutions to today's exceptional problems.
Hello, podcast fans, wherever you may be. Todd Kolmodin again with the Gardien Group, along with Rick Meraw, in another episode of our podcast series. Today, episode 11, or is it 12? Episode 12 is sequential lamination testing and AOI and AVI. When we talk about sequential lam, back in the day when I started my career in circuit boards, we were back in double-sided boards and even single-sided boards. But as time went on, we got smarter and packages got smaller and space requirements and constraints got tighter. So they decided that we need to get as much into a circuit board as we can. And that's when it started, the term sequential lamination. Many of you might know them as subparts or substrates sometimes. And basically, it's a multiple step process where you start with a set of layers, just like any other circuit board, but you're building the circuit board from the inside out. So you'll have, maybe it's a 10-layer board, but you'll put layers 3, 4, 5, and 6 together the first time. And then you'll drill that, and you will then plate it, and that's called your subpart. Am I getting that pretty much right, Rick?
You're right on the money there, Todd. Sequential lam basically, as Todd mentioned, has to go through plating, but it doesn't go through plating. It goes through plating in multiple steps, maybe a couple layers at a time, maybe 6 layers, maybe 2 layers. And then more layers. Once it's done plating and it's ready to go, you're going to put more layers on top of that and do some sort of microvia or some other combination of build, creating multiple lamination processes. So sequential lam is multiple lamination processes, as Todd has laid out. You're right on the money there, Todd, for that one.
Yeah, because what another term that started to be used when you'll kind of trigger your mind to say, okay, that must be a sequential lam, is when they talk about blind vias or buried vias. They use the term micro via, but blind and buried vias kind of an indicator that you're getting into sequential lamination. And that's when we start putting multiple parts together. Like Rick said, this includes the drilling and the plating process too.
I know a lot of companies call it sub-assemblies too.
Sure.
It's an assembly, right? It's part of an assembly, but it goes with the entire package later on. So it's only parts of an assembly, and you need more parts of the assembly to make the final PCB at the end.
Exactly. And what happens a lot of times in the manufacturing process, your sub-assembly, your subpart will have its own part number designation, and some companies have different names for them. They call them the child part or the subpart. Then you have a parent part, which is the final version of everything all laminated, drilled, and plated together. And then also, when you get into this, I put a slide together for those of you that are watching the video, that when you add in basically all of the possibilities almost that you can today, you'll have your sequential lamination process, and then microvias, possibly stacked microvias, and then you can actually even add in your embedded type of product. In the slide here, I show you even your embedded capacitor on the close to the outer layer, along with embedded ceramic or embedded resistors. So it gets really complex when you have multiple lamination processes for subparts, and then you add embedded passives. You can even add, embedded inductance as well. And this all comes into play, but somehow has to be tested. And that's where we find this challenge in ET, is testing of subparts, what the best way, because obviously you don't want to get it all done and have the wheels fall off and it blows up. So, I mean, Rick, how do we test these? What are some of the options that we can do to test these subparts, sequence parts?
Yeah, Todd. So because we're going through the plating process, you can catch outer layer defects using an AOI type of fair, but also you may want to double check your plating. So you want to double check your plating, so you need to test it. So there are many different forms of electrical test or generating test points for a subassembly. I know at Gardien, some clients require us just to test the holes because they can do the AOI or AVI on the outer layers. AOI, I mean, not AVI. On the outer layers of the sequential lam and catch any copper or broken traces or shorted traces. But then they can't do anything with the holes, so they either got to rely 100% on the plating process. And the reason why people do that is because just as a sequential lam, it's many, many, many lamination steps. It's many, many process steps too. So if you can catch a defect beforehand and make a judgment call whether you need to restart that panel beforehand, you're always better off. It's going to cost you less, but before you put more money into that subassembly. So when you generate test points, you can take Class C, IPC 9252 Class C, everything open and mask. There's no mask, so we're going to test everything on this board. So if you have a landing pad somewhere or you have copper traces that go from point A to point B, you can put test points on the end of them. You can run your midpoint optimization. The only thing is for the test points is the more single points you may have, it depends on how it's set up. You may have a little bit longer of a test cycle time on some particular tests, especially if you're doing on flying probe. As I mentioned, Todd, there's many different forms, but the biggest thing is you want to test for is you want to get your continuity. If the product's going through AOI, you know that you're most likely going to catch 99% of the opens and shorts caused by the traces. And then with electrical test, you're going to go and check for continuity and make sure that the plating is correct inside the holes. So it's not recommended for cost-wise to be putting more layers onto a subassembly panel or a sequential lam panel without doing ET. ET is going to prevent any kind of plating defects or catch them early, save you maybe remake that panel or scrap that panel. But that's one of the things that we want to do early in our application.
Right.
Now, go ahead, Todd.
Oh, I just go ahead. You seem to be on a roll there, so I'll let you keep going.
So as I mentioned earlier, we can do flying probe tests, which significantly reduces the cost of it. We also have, at Gardien, we use our Accelerator 8 sometimes to scan the subassembly and then put on flying probe. It saves a little bit of time as well. And it's not really recommended to make a fixture, but I've seen some applications where they've built big fixtures and test the full panel, double-sided or single-sided at once. I've also seen some applications where we've done 4-wire Kelvin on the subassembly as well, because they want to make sure that everything is dialed in with the plating process, especially if you're getting up there and you're making like high layer count HDI product. You want to make sure that those holes are correct in the initial stages.
Perfect. One of the things that comes to mind for me when we talk about 4-wire Kelvin, we have that solution obviously with our group and our equipment as well. What we usually see in the sequential lam type affair, once the board is done and it goes to ET, we do have the defect ratio of opens and shorts versus microvia issues is weighted towards the microvias. The bonding issues or plating anomaly or something like that. So most of the time when we see a high percentage of the time we see failures in multi-layer sequential lam product is usually tied to the subpart level. It's a void inside the board. And that's one of the things where when Rick mentioned 4-wire Kelvin, this is the type of affair where it's very, very cost effective actually to do some sampling on the subparts for 4-wire Kelvin for those microvias. And you can see those minor changes. Because remember in our last podcast, we talked about 4-wire Kelvin, we're looking at very minute changes. So your standard ET, remember, if it's class 2 or class 3, you're, looking at 20 ohms or 10 ohms for a continuity threshold. And the anomalies that might be associated with a marginal bond on a microvia, or a plating anomaly in a microvia, are not going to really show up as a final ET fault for continuity when you're talking 5 and 10 ohms. Remember, we're down in the milliohms. And so sampling, especially on a high density product that's obviously going to be a high revenue generating product, and you're putting a lot of money into building it, the little steps that you can take along the way, although that may take a little bit of time, can really save a lot of money in the end. So we also use, we talked a little bit, Rick said, about AOI, the machines used for scanning layer product. And this is, prior to plating and such. You have a little bit more experience with the AOI over the years, Rick, than I do. Maybe you can walk us through a little bit of the AOI world.
Sure, Todd. So what's interesting about the AOI, especially when we're dedicating this to sequential LAM and AOI, I guess, but it's the plating. So when you go through a plating process on a sequential LAM, you're plating over the traces as well. So whenever you plate over the traces, it's not as easy to AOI as a layer. So when you print and etch, the old style of making a circuit board, it's been around many years, so you print it, you etch it. The copper itself is very uniform. Okay, you may have some etching come into play, tolerances on the edges of the tracks, and different kinds of etching may cause some differences, but it's relatively the copper looks the same. But when you go through the plating process, in many cases, you could have some small discolorations here and there, or you could have the copper is a little bit shinier in different places. So in AOI, it's an optical machine. So it's an automated optical inspection machine where it takes a camera and looks at a panel. And in this case, it's looking for copper. So it sees all the copper on the board, and then it compares it to the CAD data within some sort of etching factor, and it would detect any anomalies that may occur. Say there's a mice bite out of the track, it's a dimple in the track, or any kind of extra copper, or any kind of water stain, or anything like that, which makes the copper a little bit different color, would also show up. But it's a visual machine. It's not electrical tests. So you're not getting current through. And we all know the whole reason why we build a circuit board or make a circuit board is to have a connection device. And a connection device flows current from one end of the net to the other end of the net. So you have to have copper connection and current flow.
Right. And I know, like you said, AOI, we a lot of times we're doing circuit layers, single layers, due to volume constraints, they don't do the plane layers. And I'm just going to take a second here that I know the reasons why, the plane layers are a lot of times deselected because of volume going through the AOI machines. And they basically take the risk. And what we find in ET over the years, that's not necessarily the best idea, because we do have, returns or failures in ET that are tied to the plane layers. And most of those are etching defects from the oxide process. Either there's a left contamination, so your clearance pads fail on some of the areas, or some of the landing pads on the plane layers. Remember, you got a lot of copper on those plane layers, and trying to get that all etched away perfect without any anomalies can be difficult. But we know that plane layers a lot of times are deselected. I mean, one of the options is get more AOI machines, or actually take the time to, maybe on very expensive product, maybe you do select those plane layers to make sure that they get scanned. Rick, when you were talking about the AOI machines, they don't necessarily, you said that they compare to CAD data and such, just like we do in ET, where we build the circuit board electronically. And so they generate the same type of files for the AOI machines, do they not, Rick?
Yeah, so it's basically the same sort of data that we start with on for ET is AOI. It's usually production data. Production data is panelized, and we take the panelized data, and it knows for each layer that you're doing, layer 2, layer 3, it knows what's on each side, and then it knows where the copper is and what should be there, and it can basically makes a comparison between what should be there and what's not there based on the CAD data, the original CAD data of the one-up. So the one-up data is just stepped into a production panel, and that whole production panel is usually programmed into AOI.
Okay, perfect. And then the other, moving along into another optical type of inspection is what we call AVI, or automated visual inspection. And AVI is rather newer for board inspection, because one of the major things for it is to be able to help the human eyeball be able to distinguish defects quicker, and helps with, the fatigue factor and all that. Rick, you know more about our automated AVI equipment that we offer. And I mean, I know the AVI stuff out there, probably a lot of it operates a little bit kind of the same, but we're kind of proud of what our machines can do. So why don't you kind of walk us through AVI a little bit?
Yeah, Todd. So AVI, the big difference between AOI and AVI is that you're looking at the finished board. So you're going to have the solder mask on there. You're going to have the copper finish, the surface finish done. You're going to have the silk screen legend print on there. So you have multiple different colors. Whereas in AOI, basically the machines are trained to look at for one color only, whether it's infrared machine or a camera machine. You're looking at copper. And for AVI, you're looking at the entire board just as a human would see it. So you're going to see all the different colors. So of course the machines have to have color cameras, and each machine can go down to a different pixel rating, whether you want a low-end machine at 50 megapixels, or you want to go down to 5, it's up to you. But the finer the pitch, the more you see. So and it's the same sort of thing, except for the CAD's a little bit more complex because you have to put everything in there. Of course, under CAD images, there's not a lot of CAD products out there that are using different colors, because with solder mask, you can have red mask, green mask. You can have on the surface finish, you can have gold, you can have hassle, you can have Entect. There's many different color, and you can have mixture, gold fingers. You can have different kinds of silk screen, yellow, red, whatever the buyer is looking for on their printed circuit board. So all this is accounted for. So the CAD images is usually like, let's call it a black and white image. So you know where all the features are. And then when you do your first scan, you're going to find out the colors of those features. And the colors of the features are what's used to pick up, once it's set up and tuned in, it's used to pick up any inconsistencies in future boards. So it's like the first couple batches or boards that you scan, you may have something wrong with the first one because we don't have a known good one for color wise. So then you may have to come back and look at the colors and just retweak a couple parameters. But more or less, it's looking for that. In the PCBA industry, Todd, they have 3D AOI machines, which are looking for component placement and things like that. But in our industry and the PCB bare board level, it's just a 2D camera, but it does detect color, and it does a comparison to the CAD data, black and white image of the CAD data, and you set the colors when you do the first scan, and you set some parameters based on some features. So you can do your annular ring at this parameter, you can do your pads at this parameter, You can do your thieving at this parameter, because you're going to see under the solder mask, you're going to see the thieving, you're going to see the base laminate, you see everything. And what's interesting about, as Todd alluded to in the beginning, is the AVI, it's consistent. There are some very good visual inspection operators out there. We know this industry is mostly driven in the North American market by visual humans that are very good. They're trained our eyes over the years to look for defects in the PCB board. Sometimes very consistently, and then there's others out there that sometimes maybe it's getting towards the end of the shift, you may miss something. There's all different tricks of the trade to try and catch these defects, but what's consistent is the AVI will always catch these defects, and maybe it catches some defects that you don't necessarily are deemed bad. They're deemed acceptable by the IPC standards. So you can program the algorithms to say, if I have a dimple of a track and it's only a 5% dimple out of the track, then it's okay, or a mice bite into the track and it's only 5%. It's within the tolerances of IPC. Or if you have an extra piece of copper and it's within the tolerances of the IPC, you can set that parameter up in your machine so it catches that as well. Very similar to you do with the AOI. The same thing, but it's just done in color in the AVI machines.
Very good. And I go along with Rick there. When you're doing your inspection and fine tuning and tweaking, it always goes back to, they're building to a specification, but also, there could be some allowances or such from your customer. Always consult your fabrication drawings and procurement documents and such. And I wanted to touch on also the strength of the AVI against the human eye, which Rick said that there's very, very good operators out there. But we also find in doing some Kaizen events or things like this, checking ergonomics, that the fatigue factor is real. I mean, if you're sitting there and you're doing hundreds of boards, hours and hours, I mean, your eyes get tired. And so a lot of times you'll find in some of these events, things will come out like every X amount of boards or every so many minutes or so much time frame. You get up and not necessarily go take a break or whatever down to the break room, but you may get up and do some long vision exercise with your eyeballs and let refocus and stretch your bones a little bit. That's always we're finding more and more that we need to take care of our workforce as well. So those are good points there. And when Ricky, we're talking about this question comes up on the AVIs, what they can detect and all the anomalies that you talked about. And another thing that it can find out for you is, although the colors of mask and nomenclatures, it can also dimensionally check your board. So if you have pads that are supposed to be a certain size, it can double check that, or your annual ring is supposed to be a certain size. And another thing it can tell you if you've got your nomenclature on there wrong, like if you somehow rotated it on the board or you flipped polarity on it, things like that, that sometimes, believe it or not, can be easy to miss with the eyeball because you see the mask on there, but you didn't notice that it might be backwards or rotated or something. So all these dimensional things can also be checked by the AVI. Isn't that right, Rick?
Yes, that's correct, Todd. It can be, as I mentioned, it sees everything. Some of the fine inspection measurements cannot be done, but a lot of them, I'd say 80% of them, can be done using the AOI. The AOIs usually go through in some sort of speed, and sometimes the speed may vary the dimensional part a little bit, Todd. But other than that, the machines can measure. They can measure not as accurate as like a hole measuring machine and types like that, Todd, but they're not bad.
Well, I didn't want to get too far out there. I wanted to double check with you before I overstated some capability. I know that some of the machines out there that today that you can combine both the AOI and the AVI into one machine where you can basically do layers and then you can do final board all with the same piece of equipment?
Yeah, that's correct. As I mentioned, the only real difference between AOI and AVI is the colored cameras. So if you wanted to use colored cameras to do AOI, and the software's takes a little tweaks here and there. There's some minor changes in software. I'm sure the programmers would say a lot of changes in the software, but it is possible. And there are machines out there in the market. As we were talking about earlier, Todd, most of the AOIs and AVIs in the market right now are single-sided, but there's a small percentage of them now. It's growing and growing as people start to automate their plants, but there are dual-side AOIs, dual-side AVIs, and a lot of them, even some of them coming with inline. So you have coming off of your plating line, you can have AOI right there, or etching line, you can have AOI right there doing inspection on your layers or inspection on your final. And then to have some sort of identification on that panel, and then it would go into a verification room where you have some verifier operators just double checking if there'll probably be some false calls. There'll probably be a lot of good panels, but the false calls still need a human to look at and validate. And if it's not right, then you can push a button and kick it off the automated line to go for a closer review. But all that is starting to come in the PCB world, and it's nice to see a lot of plants spending money and automating. It's nice to see.
Yeah, I like the automation is getting stronger and stronger in the industry, and that's good to see. I mean, defects start going down when you nothing against human operators, but sometimes machines do a little bit better, and that's great to see. So take it away a little bit from what we talked about today. Electrical test of sequential LAM subparts is getting more crucial. And one of the things that I know that the high-speed boards, Teflons, things like that, where you're getting the high-speed networks, and then you've got microvias. I mean, it really makes a lot of sense to test these subparts prior to your final lamination. We can test inners as well with our equipment, as well as the sequential parts. We talked about earlier that we can expect a higher test point count on these subparts because they're just subparts. Some of it has been drilled and plated, but you're going to have a lot of orphan pads that are still on the surface that have no functionality at this point, but they should be tested, for discontinuity or shorts to adjacent pads, traces. So it could cause some extra test time on the prober, as Rick mentioned, and it could cost a little bit. You need to do some extra thinking when you're doing a fixture design for it if you're going to go that route, how much of a risk you want to take, risk analysis there, if you want to test those orphan pads or not. We don't guarantee that, testing in the sequential cycles are guarantee a final product that's going to be conforming. Remember, we're only testing the sub, and I can't stress enough on the 4-wire Kelvin idea of testing against those microvias or those very crucial interconnects that are going to be laminated again. And what else? The AOI machines we talked about a little bit, they're predominantly used for interlayer test and single layers. We talked about how the cam generation, the rasterization works on that, and we're only validating circuitry for the layers scanned. And as Rick mentioned, we're doing that visually. The circuits that we're verifying are visual only for breaks and anomalies, mouse bites, dish downs, things like that. And we should use these on, this is still Rick and I talking, but, if it's a very high complex board or high dollar value board, consider testing or scanning the plane layers as well, especially if you've got split planes on a layer. You've got a lot of copper on there, a lot of clearance pads. You don't want primary plane on a split plane, primary shorting to secondaries and things like that, because that's just a heartache and scraps the board immediately if you don't catch that until the final board. And use of the AVI provides relief for the final QA people, the labor burden they have. The double-sided high-speed scans can go for multiple defects. We talked about a lot of those. And high resolution cameras can catch defects down into the microns. It all depending on how much you want to, if you're looking at entry level machines, single camera, double cameras, color, and all that type. That's all a process that, you can talk to your vendors. And, if you really want, if you're, looking into this type of equipment, definitely drop us a line. We'd be glad to, our sales guys, Jason, be glad to talk to you. Rick can talk to you about it too, about our AVI possibilities and what we can offer for you. And with that, I think we're about done. I kind of stole the show on the conclusion, Rick, but do you have anything to add to kind of summarize our little talk about subparts and visual scanning?
So if you're making a sequential LAM, Todd, I can't state it enough, and you want to make sure you have a final product that's reliable and good, I would strongly recommend that you do the ET on the sub part just to validate the plating. I know you can do it all the end, but it's just a cost saving measure. I think the hour or two you'll take on a lot to do it is a lot less painful if something happens later on down the road, a week or so later, when you got the board ready for final ET and then there's a problem with this sequential LAM step. That's all I could recommend. I can't stress that enough, Todd. There's more to AOIing us. It's more to sequential LAM test than AOI. I strongly recommend that you do ET on it as well.
Right. I mean, there's books out there. I mean, we took 20 minutes to half hour talking about this subject, but there's entire volumes of books written on the lamination process and micro vias and buried and blind vias that's out there. But if you want to know more about it, just drop us a line at info@gardien.com. That's info@gardien.com. And check our website for our podcasts and information should you decide that you're looking for equipment. We'd be glad to help you with that. That's www.gardien.com. That's www.gardien.com. And our podcast, look at your favorite platform. We release through Buzzsprout, and they should be available on Apple Podcasts or wherever your podcast favorite may be, and you can also find them on our website. For Rick Meraw and myself, thank you for joining us on our Sequential LAM and AVI AOI podcast, and look for us again on our next one. I think coming up, we'll be talking about functional fixtures and hybrid designs, and we'll have a special guest speaker from our Denver facility, Stephen Reedman. So look for that coming up shortly. And with that, you all have a great day.